My name is Daniel Haraldsson, and I will present the project that I have implemented during the real-time systems course. The topic I'll be handling today is hardware acceleration, and the task that I wanted accelerated is a simple pixel manipulation for image processing. So suppose that you have an image containing of several pixels, and for each pixel you want to apply some form of operator. This could be add a constant to it, or multiply the value with another constant. It could be perform some form of nonlinear operator on it, like taking the square root, or perform another form of image stretching of the space we're working with here. This is mainly relevant for several applications, mainly the intent, or the specific implication that was implemented here was image normalization. So you have an image where the color space is somewhat compressed, and you're not using the entire range of the image color space. That so applying an operator to all the pixels might make you able to put it to the edge and stretch it out, so that you get more of the so that you can present the information that is in the image better. So what I want to do during this project is to implement this transformation function, which relates the initial pixel value to the new pixel value in this case normalized image. Now, if we look at the block diagram of this system, it consists of two main domains. We have everything implemented in CPU domain, and whatever else implemented in the FPGA domain. These are the main functionalities. We also have some GPIO handling and implementation in the FPGA, but that won't be gone too much in depth with, since it was just mainly debugging tool. The function that we explained earlier was implemented twice, once in the FPGA and once in the CPU, and the task was implemented in the FPGA using the HLS software, which mainly took as an input whatever a function or a top function written in C or C++, and then it compresses or synthesizes it. It builds it into an IP core, which Vivado can easily use for your FPGA implementation. The CPU contained the task implemented in C++, and then a task which mainly communicated to the FPGA with an AXI-like connection, sending the relevant information and then afterwards receiving the result. This added communication also adds some overhead, which might result in an added delay or an added execution time, but that will be shown later exactly how significant this added overhead will be to the performance of the hardware accelerated system. This right here is our hardware accelerator, and this is what it would look like if we never used the hardware accelerator in the first place. So what we will do is to take the time it takes for this task to execute 1,000,000 or 100,000,000 iterations, and then we will do the exact same thing for the core system, or the system that was never hardware accelerated in the first place, which should make it easier for us to compare the two and see whether if the hardware acceleration actually presents an improvement. Diving into the code should reveal that if we look in the C code, or the code which is executed on the CPU, this would constitute the image normalization. It takes the data, displacement, and scalar, and then it simply just uses it to transform the result into, or the data or the pixel value into the new pixel value. And then in the end there should be some additional clamping to make sure that there is no overflow, or if there is an overflow, that it is handled in the proper way. This exact same function is also implemented in hardware using the Vivado HLS tool. Here one should see that the function is the exact same, but there is some added pragmas here and there. There is a pragma here, or a section of pragmas here, which defines the interfacing between the remaining part of the hardware and then the IP core which will be created here. There's also a pragma here which was mainly inserted for optimizational reasons. So this is just an implementation of how to do a multiplication in just one clock cycle instead of several. If the code is run and the synthesis will be seen here, we see a lot of information. Mainly, it should be noted the target time here is the period between each clock cycle of the FPGA, which apparently, or which I could see on the FPGA, it was set to have a clock frequency of 50,000 or 50 megahertz, which was significantly lower than what was on the datasheet. But I set it here since this was what the tool showed, and then the tool simply optimized based on this. So the target time is the deadline for the propagation of the signal through all the hardware that will be implemented. The estimated time is how long time it is expected to take, and then the variance or the uncertainty is what should be added to the estimate to make sure that this addition still remains under the target, which it does in this scenario. So this should indicate that the data will get out of this IP core should be reliable in all scenarios. Also, you can see the latency. So from the first, or from the clock cycle where it receives the start signal, and then till the time where the final, or until the time where it can read the solution of the function, or the output of the function, should be at a latency of 2 clock cycles, which is expected to be significantly smaller than what would be implemented in the C code here, since it consists of several lines and several operations. It should be expected to take around 10, maybe more clock cycles here. What can be seen here is the implementation of the electronics in the FPGA. This implementation consists of the sync chip, the add counter, which is the IP core generated from the HLS tool, and Xi GPIO connection as well, and the remaining blocks are mainly there to make sure that the connection between the chip and the FPGA components is possible. So for testing, the program was split up into 2 sections. In section 1, the CPU was tested, and in section 2, the FPGA code was tested. And it was set up so that when the CPU was running, it set an LED to light, and then when it stopped, it closed it again. And then this was repeated again for the FPGA, but with a separate LED. If we run the code here, then it should be seen here on the FPGA that the first LED here, which is the time the CPU takes to solve the task, and then the next LED, as we saw swiftly there before, was the time it took the FPGA to do the exact same task. So if we try to run this code, then we should very well see two LED lighting up distinctively, as we can see the CPU part here running, and then the FPGA running here. And as we look at the signal here, it's captured, and when we see the duration of the CPU or the CPU runtime, it is set up as, or it can be seen that the CPU takes right around 5 seconds, 4.98. And here's the signal for the program when it's run over the FPGA. And if we look closer at the execution time here, it will focus. 869.99 milliseconds, which is significantly faster. Now, two tests was run. One test was to see whether if you, in the specific application where you only need to perform one of these T computations as presented in the code, and the other one was if you in the code simply computed this T computation 100 times. And then the task was just to compare how the execution time of completing a lot of repetitions of this task. So that was mainly what was done here. In the test that we just saw before, we saw the result of the test 2, which was 1 million iterations of 100 T computations. So what we saw in this scenario was that the FPGA was able to perform the entire task in 0.86 seconds, and the CPU was able to do it in 4.8 or 4.98 seconds, practically 5 seconds. What this tells us is that the FPGA is operating significantly faster than the CPU in the scenario where the number of C computations is large. If your task is significantly large and then implemented in hardware, then your hardware will outperform the CPU. However, in test 1, we also tried to do 100 million iterations of simply just one T computation. So the amount of work should practically be the same. However, the FPGA is going to suffer because it's supposed to have this added overhead between the CPU and then the FPGA using this AXI connection. So it both needs to format the data in the AXI connection. In all the iterations, it has to format the data, it needs to send it away, it needs to wait for, or it needs to signal for the process on the FPGA to start, and then wait for the result to come. So there's a lot of overhead in the process of transferring a task to the FPGA or executing a task on the FPGA. And what we wish to see here is how the FPGA gets punished by this significant reduction of both the task it needs to execute and then the number of iterations it needs to execute this for. So here the FPGA takes 8.6 seconds, or practically 8.7 seconds, and the CPU only takes 0.8 seconds to do this. And what can be taken away from this is that the task that is implemented should be sufficiently complex in terms of computational time in order for it to be beneficial to compress and put down on the FPGA, at least if you're supposed to use an AXI connection, or in this case the AXI light connection. Simply because of this added overhead and all these signals that needs to be both set and and the slaves that needs to be managed should all be handled by the CPU. So it might not have to solve the task you gave it, but instead it needs to spend a lot of time and effort in making this communication between the FPGA and CPU. So what can be concluded from this test is that the hardware accelerator is working faster than the CPU. Furthermore, the hardware accelerator was tested in terms of whether the result was correct, and that is also the case, both in the first and the second test. And lastly, it should be concluded that, again, if you want to do a hardware acceleration, the task you want to accelerate should be sufficiently large in order for it to be beneficial. It's not enough just to make it faster. It's not enough just that the FPGA can make it faster. It should also be faster. The gain from implementing it on the FPGA should outperform the drop in performance that is caused by this added interfacing complexity. So yeah, this was basically the conclusion of the project.